Hi, just want to gauge the audience a little bit. How many of you are familiar with, let's say, the term machine learning? How many of you are actually doing research or development work in machine learning? Okay, good. How many of you have, let's say, papers or something like that in ICML or KDD type conferences? Okay. How many of you is familiar with the term anomaly detection? Okay. All right. I think I can kind of accommodate this audience here. So we are going to talk about a particular algorithm called LERAD. And OK, there's no advancing here, so let's do this. OK. We talk about a learning algorithm called LERAD, and it's a randomized algorithm. And what its purpose is to learn rules that represent normal behavior and detect anomalies accordingly. I'll go through what anomaly detection means a little bit. Let's say in a security framework, it doesn't have to be security. I mean, it can be anything. You just differentiate what is normal and abnormal. It could be let's say a shuttle flying up, and what's normal behavior of the shuttle? Or your car, what's the normal behavior of the car being driven on 101 or something like that? By the way, on the way to here, there was an accident, and I almost got stuck. So I guess that could be an anomaly. Maybe it's not in California. I mean, it happens all the time. I don't know. There were helicopters flying and stuff like that. I was like, I guess I'm not going to make it. So first of all, let's from an intrusion detection perspective, as in a security perspective, there are majorly two approaches of attacking the problem. One is usually what you get on your computer with like a virus scanner or file, virus scanner mostly, that basically it knows about what the attacks look like. You store it in a database, and you just match what you get with the database. Okay? So you're modeling attacks. Okay? You're not modeling the bad things. So generally, I have a laser here. Generally, for that approach, you cannot detect new attacks. For example, your virus scanner, when a new attack comes, what happens? So you probably know that. So anomaly detection is another way of approaching the problem of intrusion detection. Instead of modeling attacks, now we're modeling normalcy. Okay, what's normal behavior of the system? And then identify things that are deviating from your model. Okay, obviously, that model can be handwritten, but in a more in a CS way, probably that you want to apply machine learning or data mining techniques to generate these models automatically. And that's the focus of the talk today. And obviously, that it can potentially detect novel attacks. That's the main advantage of it. Okay. So it doesn't know anything about attacks. It just knows about basically normal behavior. So anything that is deviating could be novel, could be old, could be existing, could be new novel attacks. Unfortunately, one of the drawbacks is that the false alarm rate is high. As in that it's deviating from the normal behavior doesn't mean that it's bad. Okay? So these two approaches are pretty complementary to each other. And I don't think that one can replace the other one. Probably some hybrid approach later on would be a good thing to do. In intrusion detection system, it depends on what kind of data you are looking at or analyzing. You could be on the host space side. That means you're looking from the OS perspective or looking at the application perspective. Or you can on the network side. That means that you're looking at network traffic, packets, connections, stuff like that. There are a couple of algorithms that are already in place. I'm not going to go through that. The slides will be available at Tech Talks database anyway, so I'm just going through a little bit quicker here. One of the key things that in the algorithm is trying to approximate certain probabilistic events, which are anomaly events. So for example, let's say that given some data that has no attacks, so it's all normal, what is the probability of certain event X happens? Okay? The central idea here is that what is that probability? Okay? So given training data that is normal, I'll approximate what that probability is for event X. Now, if X was observed during training, then you can approximate it using standard techniques. What happens if X was not observed? Okay, so if it wasn't observed, what is the probability of something that you never saw before? That's a problematic issue to address. So sometimes I call it a zero frequency problem. You never observed before. How are you going to estimate that probability? So remember that we are interested in the likelihood of anomalies. That means things that are not normal, things that you might not have seen before. So let's back up one step with a kind of a simple example to help you understand the problem and how you can estimate that in some fashion. Consider like sequence number 1 here. You have A, B, C, D, E, B, F, G, C, H. Okay? Now, we want to estimate something that we have not seen before. Okay, let's say the letter Z. Okay? It's not in the training data. So what's the probability likelihood of that occurring? Zero frequency problem. You haven't seen it. What is the probability? Okay, let's look at sequence 2. You have AA, BB, BA, BB, AA, things like that. So there are 2 sequences here. You have the same question. What is the likelihood of seeing an unseen Z? Okay, now I'll give you like a little question here. Which sequence has a higher likelihood of seeing Z? Okay, this is sequence number 1, sequence number 2. And we want to estimate the likelihood to see something brand new that you never saw before. So we don't need to have an exact number, just by a gut feeling, or you can apply complex mathematics in your head as well. So is it sequence 2 or sequence 1 has a higher likelihood to see something brand new? Is the question clear first? Okay, it's clear. So I'll give you 10 more seconds. Think about it. We'll take a vote. Okay, who thinks sequence 1 has a higher likelihood to see something new? Good. How about sequence 2? Okay, very good. Sequence 1. So someone raised your hand, and can someone explain to me why that's the case? Yes, please.
It has more values already.
Has more values. Okay.
Yeah, more different values already. The other one only has 3. The length would also matter, but they seem to be same length.
Okay, good. Very good. So basically the first one has more letters. We can think about that. Another way of looking at it is that this is more random than this one. This has some sort of pattern, say A and B are repeating. So you have a higher likelihood to say, I'll expect A and B after that. And so, yes, so intuitively that you would say sequence 1 would have a higher likelihood to see something new. Okay? So let's say apply Laplace smoothing, the add 1 technique. So this turns out to be, don't worry about this exact number here. I just want to show you the relative ordering is not what we want. So using Laplace smoothing in a certain sense, it's 1 over 19 here, it's 1 over 13 here. So sequence 2 is higher than sequence 1 in terms of observing a new event. So this is not what we want. So another way of estimating the novel probability is R over N. R is the number of unique values in the training data. N is the total number of observed values. So the more you have observed in terms of unique values, then you have a higher likelihood to see something new. So obviously you want N to be large sample so that you can have a better approximation. This is due to Witten and Bell. So in our example here, the sequence 1 and 2, there is 8 over 10. Obviously, 8 over 10 is a way high probability, but you can think about this sequence is very long, like 10,000 million, then this would be a more approximate, a better approximate. So here, you can see that in our case, R over N here, 8 different values, 8 unique values over 10 events. Here's 2 over 10, so obviously sequence 1 has a higher likelihood, and this coincides with our intuition, with the sequence 1 should have a higher likelihood to see something brand new. So basically, we kind of touch on the problem of zero frequency problem. You haven't seen anything like that before. What is the probability? Okay, this is one possible way. There are many other ways. As you already point out 2 ways, so there are many other ways. So this is a very simple way to approximate it, and with the direction that we want to. So now, given that, how we can, that's the basic idea behind zero frequency problem. And we want to approximate not just a single event, but we want to also condition on certain other events, not just like a prior probability, but like conditional probabilities, okay, posterior probabilities. Let's say that we can look at just approximate certain event called Z, or you can approximate certain event Z given certain other event, or you can, even better, that approximate some event given a bunch of other events, A, B, C, blah, 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 blah. Now, in intrusion detection, let's say dealing with network data. Let's say that one of the attributes is IP addresses, right? Okay, so how many possible IP addresses are there? Let's say not worry about the new IPv6 yet. Let's say the regular OIP. How many possible IP values are there? About 4 billion, 2 to the 32, very good. So just one attribute, okay, let's say A here, one attribute is 4 billion combinations. Let's say you want to model source and destination address. So B is the destination, well, A is source, B is destination IP address. So you got 4 billion times 4 billion, so it'll be 16 what? I don't know, trillion, quadrillion, no, more than trillion. 4 billion times 4 billion combinations. That's quite a large number. I think Google always deal with large numbers here, right? So probably not at the Google level, G-O-L-E, no, how do you spell Google? The real right way, G-O what? G-O-L. G-O-L? G-O-L-O? Never mind. So you know what I'm talking about, the right way of spelling Google. Anyway, so there are a lot of combinations here. So it's not easy to jump from, let's say, these kind of probabilities to up to these kind of probabilities. Okay? There are a lot of combinations of events. Okay? So then we need to do something a little bit faster. Okay? So we're going to look at an algorithm based on sampling techniques that we don't need to actually estimate everything, the 4 billion times 4 billion times 4 billion type things. Okay? So we only need to look at the regular occurring events to model null behavior. Just only pick the ones somehow to estimate these probabilities. So we don't need to actually estimate all of them. So LERAD is an algorithm to try to sample some of these, or some of the important ones, so to speak, to approximate. Before we talk about the algorithm, we want to talk about the output. Okay? The output is something like the attribute that we saw before. Okay? And it implies certain event, the Z that we are approximating, is an element of these values. Okay? That's what a rule looks like. Now, this is different from association rule, if you know about those things. Instead of, here, we allow a set of values instead of a single value. Association rule will allow only a single value. It's also different from the classification rules because this is not a fixed attribute. If you know about classification rules like Ripper or C4.5 rules, those are particular classes that are predetermined to be the right-hand side, the consequence. So first of all, I want to point out the output, quote unquote, the rule semantics is different. Now, what does a rule mean? What's the semantics of a rule? So this is a rule, and actually, what we are trying to estimate is that given the antecedent, what is the likelihood that it's a new item, a new value that we have not observed? Think about that. These are the values that we have observed, the A, B, C previously. So it's not in one of these. That means a novel value, the zero frequency type thing that in the training data. So we estimate that by using the R of n, the little approximation formula that we use. R is the size of this set here, so how many unique values there are. Okay? So n is the number of instances or events that satisfy the antecedent. So the rule looks like this, and basically we are trying to approximate this particular probability, okay, by using R over N. So the algorithm looks like this, okay, in a very simple way, a simple create candidate rules, okay, using a randomized algorithm. We'll talk about it a little bit on quickly. Score, somehow ranking them and deciding that which might be better than the other ones. And then we're going to remove some of them, okay? This is based on a training sample to speed up the learning, okay? And here that we're going to update the rules saying that using the entire training set. And at the end, we're going to validate, see whether these rules are going to be really good at prediction. So we'll try to evaluate its performance on an unseen validation set. So the first step is to create the candidate rules. So the first thing it does is it randomly pick two things, let's say two instances, okay? And then if, let's say that these two instances are here, A1, B2, C3, D4, or D6 here, then we find the attributes that are matching, so it will be A, B, and C. And then we create different combination of rules that's based on the matching attributes. So in this case, since A, B, C are matching, so we can make either A, B, or C to be the consequence. And the two attributes will be in the antecedent, accordingly with the same values. And you see here is a question mark later on, because a set of values, we're going to fill this in later on. Now, the mechanism is very simple. But why do we want to do this? Why do you think that if I pick two things out of a big pot, so to speak, and if they match, then I will see more of them? Why is that? Actually, I gave you the answer, or I should have asked it a different way. But let's go back. Forget what I just said in the 5 seconds, last 5 seconds here. Okay, think about, okay, let's say you have a big part of, okay, Google likes colors, right? You have blue, orange, yellow, green. Okay, you have all kind of color balls in a big jar, right? Your big candy jar or whatever, okay? And the candy jar is not transparent, it's not clear, it's dark, you cannot see anything. You randomly pick out two balls. And they are both red. What can you say? Not much yet, okay? Let's say you randomly pick again, there are two balls, and they're also red again. What can you say now? Let's say, a lot of red balls, all right? So if you randomly pick something, and you don't know what they are, and they match, the more times you do the same thing again and again, you have a more and more likelihood of expecting that more of those things are around, okay? That's a primary idea behind this simple mechanism. Basically, you pick two things. And then basically, the more they are the same thing, then you expect more of them. Okay, so let me give you the backside of the, let's say that the candy jar you have has like millions of candies, and there are only two red balls. Let's say 1 million balls, and two of them are red. What's the likelihood of picking two red balls? Very slim, right? Okay? So the idea is that, so the flip side is that if it's very small amount, it's very unlikely to pick two things and they are going to match. So that means that there will be more of those. Well, not there will be. If you are very, very, very lucky, you can still pick two red balls out of 1 million other colored balls, right? Well, probably you can win the lottery too. So you could do that, but the likelihood is much less. So if you randomly pick two things and they match, there's a higher likelihood to see more of those around. So again, if they match, there are more lying around, potentially, not definitely. So we create these rules to capture that potential patterns, as in they might occur more and more often. Okay, so then we use a training sample to estimate how good are these patterns. Now, how many of those exist, as in how many times 2 red balls coming out a lot of times. So look at these rules here. It's the same 3 rules. Now we update with the sample, training sample. And we calculate that how many of those are 2, 3, 4. We fill in the values. Remember that it was a question mark beforehand. Here's a question mark. Now we fill in the values based on the observation in a sample of the training data. So how likely they are matched. So they're matching, let's say in this case, n again is the number of times it matches, so basically. So that here n is 100. That means 100 of these things around based on the training sample. Okay? And out of these 100 samples, the variation is pretty low. It's only 3 possible values in the consequence. So a lot of, let's think about this is a color or something, and this one is another attribute, I don't know, the size, big or small, or something like that. So it's only a few sizes that you can see, but the colors are the same. And there are 100 of those. Okay? Obviously that the bigger n is, the better, relative to R. So we want n to be big, so that means more times that those are matching. And that R is small because we don't want this to be a huge set. If there are 100, let's say 200 matching pairs and they have 200 items here, then that's basically everything is unique in terms of B. So we want large n, small r. So the larger that score is, n over r, the better it is. So basically the flip of the zero frequency probability thing. So after we have some score, estimated score based on a training sample, then we look at how we can actually reduce the number of rules that we can throw away and concentrate on the high quality ones. Again, basically high quality probabilities that we want to estimate. So we already talked about high scoring. There's something called redundancy check. Some rules are, or some rules subsume the other ones. So you don't need the other ones. So you need the more general ones. You don't need the more specific ones. And there's also coverage check. We'll talk a little bit more. So these 3 things can eliminate some of the things that we need to consider. Let's look at redundancy, as in that some rules might be more general than the other one, and you don't need to keep those more specific rules. Let's look at rule 1 and 2 here. So rule 2, they have the same consequence here, and rule 1 is more specific than rule 2. This is a more general condition. So rule 1 is actually redundant, so we throw it away. We don't need to worry about that. And let's say rule number 3 is like this, and 2 and 3 don't really correspond to each other, so we don't worry about that. Let's say rule 4 is something like this, then rule 4 is more general, and then we kept that and throw away number 3. So basically just you keep the more general ones and throw away the more specific ones. The coverage check actually includes the redundancy check. We don't need to perform that check separately. So the last step here actually does everything. I just want to illustrate the idea. So first, the first thing that we need to understand is that in order to realize what the coverage test is checking is that, number one rule, you want to be covering as many examples as possible. That means a general rule. That means certain pattern exists across potentially many instances. However, a tuple or instance or event does not need to be covered by multiple rules. You just need one to explain that particular tuple instance. Okay? You don't need multiple of them. So that's the coverage test. That's the major motivation of what we are doing in the coverage test, or the reason of doing it. So the algorithm is a relatively simple, greedy algorithm. We check the rules in descending order. So the higher score one we'll consider first. So for each rule, then we mark the currently unmarked tuples that are covered. Okay? So if the rule covers new tuples, then we keep it, basically. If there's no new coverage, we remove that rule. So that rule does not help me explain the data. there's already a previous rule that explained the data. So there's no new coverage. And we can show that actually coverage as substitute. So basically, the coverage check does all three things that we were talking about earlier, like higher scoring here, redundancy, and actually coverage check. So that helps us minimize the rule set. One important thing that probably Google people knows is that if you are dealing with large amount of data, you want your algorithm to be fast, right? So if you have a huge amount of rules to check against data, that will take a lot of time. So we want to minimize that, okay? So that will basically help efficiency purposes. And the final training basically is saying, instead of looking at the training sample, now we have a minimal set of candidate rules, okay? And we basically finalize what the N and R values are, populate the consequence, how many possible values there are. So update the consequence, the values here, and update the score, which is N over R. So the final step is validation. So actually, the training is only 90% of the available training data, or whatever percentage we can choose. And then actually 10% is for validation. That means that it's not available during the rule generation phase, just what we talked about before. Okay? So remember that all the data is normal. Okay? Assuming all the data is normal in the training. That means the validation set is also normal. So if any of the data inside the validation set, the 10% that trigger a violation of the rules, that means that rule is not generating enough. That means overfitting. So if the data item causes a violation of the rule, basically it's a false alarm. Remember, in the anomaly detection, false alarm is a big problem. So here, this step is not guaranteeing, we're trying to reduce the false alarm rate. Okay? So what happened to things that you never seen even in the training data? What do you do with that? So here, we take 10% out, that the training data, the rule generation algorithm hasn't seen before, see whether we can break some of those rules. If you break some of those rules, those are removed. I'm going to go directly to the experiments. The DARPA data set 99, there was basically a evaluation back in 99 by DARPA by multiple projects and stuff like that. We used week 3 as training testing for 4 and 5, weeks 4 and 5. So that means the validation set will be part of 10% of week 3. These are some of the sizes here of the training data. What are the attributes that we use? First of all, there's a version called LERAD TCP, which look at TCP connections. Okay, we assemble the packets, or we assemble the connections based on packets. We look at the last 2 bytes of the destination address, 4 bytes of source address, and port number, duration, length, TCP flags, and payload. Okay, usually most of the algorithms they don't use the payload information, only the header information. So this is one of the few work that actually does that. And for all here, we also look at UDP attributes as well. So all the attributes in TCP as well as UDP and ICMP header fields. Results. During the DARPA evaluation, they dictate that you cannot have more than 10 false alarms per day. Okay, it's reasonable. They were thinking about reasonably that a system admin would be able to handle 10 false alarms per day. There are totally 201 attacks. 74 of them are hard to detect, defined by Lippmann. Basically, those are attacks that were not detected by the evaluation participants well. Mostly, okay, new attacks or variation of existing attacks that the current participants could not, at that time in 2000, or 99, that could not detect. For LERAD TCP, based on TCP attributes, we detect about 58% of those. We also, more interestingly, detect 60% that the other system cannot detect well. Okay? And we have similar numbers for LERAD all, that means using UDP attributes as well. The best, quote unquote, participant during that evaluation was called expert 1, okay, according to the paper. And they detected 85, about 42%. So we did better. However, we need to be a little bit more cautious about these numbers are not directly comparable because we are able to run the test multiple times. But they cannot. They basically, it's a blind test. They submit their results. However, most of these systems are based on signature-based systems. Okay? That means they have knowledge about text. In our system here, there's no knowledge about text. It's totally pure anomaly detection systems. So we don't know anything about text, can still detect more than they do. That's probably a significant thing to think about. Now, we talk about efficiency. Now, some of you might have heard of STAD as an IDS. How many of you have heard of STAD? How many rules are there in STAD? Ballpark. 2,000, good. Our LERAD rules, again, it's not basically signature rules, right? Specifying a text. We learn about 50 to 75 rules. That's 2 orders of magnitude lower than someone just gave me an estimate of SNOT rules. Okay? So you can tell that it can be a very efficient system. Okay? There are some other numbers here, probably not very relevant because this is, you have much faster computers and stuff like that. So this, or much more data and stuff like that. So, so we can do it in minutes with gigabytes of data. So yeah, starting with gigabytes of data here, dealing with minutes here, and then we can actually do the detection time and training time. Those are in seconds. Now, part of the KDD talk is looking at during the validation phase, we actually throw away rules. Remember that we want to reduce false alarm rate, which is a very big problem for anomaly detection. So, since we don't know anything about the bad things, so false alarm can happen very easily. So we remove. So, however, remember that we have a coverage test that minimizes the number of rules. So if we remove some of those, that means we're removing coverage. That could, although we are reducing the false alarm rates, but also we might also increase the misdetections, as in reducing the detection rate. So we figured that, if we spend so much time, not so much time, some time in reducing the set to be 50 to 75 rules in that particular experiment, by throwing some of them away, then you're getting really few rules. So that might not be a good idea. So instead of pruning all these rules, we keep 50 to 75 rules around, but we weight them, as in that some rules are more important than other ones, or more trustworthy than the other one. So instead of basically pruning them, we violate the rules, decrease the weight, okay, not throwing them away. So you can say, if you're throwing away, basically assigning a weight of 0. And then if it's conforming, it will basically increasing our confidence, increasing our trust to that rule, then we increase the weight. A very simple idea. I'm not going to go through all the algorithms, but a simple one called window. So basically, you have 2 parameters, alpha and beta. Alpha is a penalty, as in that if you cause false alarm during the validation phase, then I'll decrease the weight starting from 1 down. So alpha is something between 0 and 1. Let's say that if you conform, as in that the rule is not generating false alarm, you increase the weight a little bit. Another way we look at it is another algorithm for assigning weights is that we want to look at the weight total sum for penalty and reward. We want them to be equalized, as in total amount of reward is the same as the total penalty for all rules. So we first calculate the total penalty, TP here, and then distribute the increase by the number of, by the penalty. So we calculate first the total sum of penalty, and then reward evenly to all rules that were good rules. So the bad rules, you have some total penalty, and the good rules, we distribute the same amount. So more details is in the KDD talk in, I don't know, on Tuesday or something like that. Okay, this time we're going to look at multiple data sets in addition to the DARPA data set, network and host data. So this ID eval is the DARPA data set. That's a university one. I think that's the a local network data set. Host-wise, there's also University, or it should be UNM, University of New Mexico, and also us and University of Tennessee at Knoxville. This is system call data, and this one is a scripting commands in Windows. How we evaluate is based on the ROC curve. Anyone familiar with ROC curve? Okay, so ROC curve, x-axis is false alarm rate, y-axis is the detection rate, and the area under the curve, the larger the better, basically. So area under the curve, the larger the better. So here, these are the three. The pruning here means the original algorithm here. The window is the first weighting algorithm. The second one was the equal weight algorithm. These are all the data sets here. So the last column here tells us that how many times that this particular algorithm, this weighting algorithm, beats the pruning algorithm. So here you can see that 5 times it beats the pruning algorithm, 1 time, and then 3 times worse. And here they are actually 6 times better. So in this particular experiment, it seems like equal proportioning is doing better in terms of weighting. So you can see that in general, that weighting is better than pruning in this particular experiment. So based on multiple data sets here. Now, we also try to understand why are we performing better in these experiments. Okay, there are 2 possible explanations. One is what we were predicting, so to speak, is that because pruning removes some of the rules. Okay, instead of removing them, we're just decreasing the weight. We actually we look back, look at the rules, whether they were removed or not, and then decreasing the weight. And we find that we have additional 18 new attacks based on this particular reason. There's also additional reason is that although the rules are being kept by pruning, as in they don't generate false alarm during validation phase, but we also increase their weight. That means increasing their confidence or the trust of that. So that actually has a little contribution. So the most of the contribution is based on what we were hoping for. Contribution coming from not throwing away those rules, but to decrease their importance. Okay, what's the time? Oh, good. Oh, there's a clock right there. All right. So another more recent work is looking at mobile data. Let's say you have laptops, you have cell phones. What happens if the cell phone is stolen? Okay. What happens if you have a spoofing attack on your MAC address? Someone is masquerading you. Okay, running around Google campus pretending to be you using your MAC address. Okay, which is easily done in these days. So the question here is that can we look at your spatial-temporal behavior and detect whether there are anomalies in those behaviors? So spatial-temporal means time and space. So basically, based on your movement, so it's not looking at the network data or the host data. Now I'm looking for geographical locations with respect to time. So the answer question is that can we come up with some approach, come up with some techniques to detect anomalies based on your geographical locations with respect to time? And we look at it from a probabilistic viewpoint. Let's say that there's a spatial distribution that you train during the training time. Okay, so DT here is the certain day of the week. Let's say Monday, Tuesday, Wednesday, something like that. T is the time. Let's say hour. Like right now, it's 11 a.m. or 12, or between 11 to 12 or 12 to 1, something like that. M is a particular mobile device, so a particular device like your device, okay? A cell phone or a laptop, okay? Mobile device. And This is basically during training time, so what is the probability distribution based on the training data? Now, let's say during detection time, we want to estimate that based on your current location, how likely that you are supposed to be there based on the training. So we look back from the current location back with some window size called W here, with, let's say, double instances. Let's say 5 minutes is one instance. So you have 20 minutes, then you have 4 instances or something. So you look back at window size. So LC is the current location with respect, and then the previous location you just were. So this is a joint probability. We want to find out the current location and the previous location where you just were before, how likely that is the case. Okay, following the textbook chain rule, so this is joint probability. You can break it down. You can break it down into the conditional probabilities, and then your LC based on the previous up to the last one, and then LC minus 1 based on condition on C minus 2, so forth. Standard chain rule textbook stuff. Now, all right, so we all know that this can be a combinatorial explosion again, because there are so many variables here, and there are multiple probabilities and multiple tables that you need to come up with. Okay, so there's a lot of time and space to estimate these probabilities. Okay, usually we make assumptions just like other probability people do, independence assumption. If you have Bayesian network and stuff like that, those use or naive Bayes classifier, those are making some assumptions about depending on certain things but not other things. So in Bayesian classifier, the independence assumption seems to work well, as in that just based on it with a condition or something else. So the joint probability can be expressed as just simply multiplying the respective probability at each location, not conditioned on the previous steps, basically. Okay? So just remember quickly. So here, what we did, if you make a naive assumption, basically each location is independent of the previous location, then you're taking out this part. Okay? The conditioning is gone. So because this is not dependent on the previous location, we can take it out. So all these are taken out, so that means LC times LC minus 1 times blah, 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 blah. So this is the equation based on naive assumption. So this is the probability of a certain location, okay, based on the independent assumption. Then we want to figure out what is the anomaly score, how unlikely that you are there. So basically, that the lower the probability is, the higher the anomaly score is. Okay, if you have very low probability where you are not supposed to be there, then the score is going to be high. So we take the negative log, also preventing underflow, stuff like that. So this will give us the higher the number is, the score is higher. Now, instead of a naive approach, we can use the Markov chain. Okay, I guess some of you might know the Markov assumption. So basically, that the current state is, the probability of current state depends on the previous state. Okay, this is the first order Markov assumption. You can think of naive Bayes is basically a zero order assumption, Markov assumption. So now you can see that the probability is based on the previous location. Okay, not just quickly go back again. The original equation looks like this, that LC depends on a bunch of things. So now we just cut off all except one. So LC given LC minus 1, LC minus 1 given LC minus 2. That's the Markov assumption, first order Markov assumption. So we get this, and we take the log as well, and you get the anomaly score. The lower the probability is, the higher the anomaly score is. So relatively simple. Now, however, the two algorithms that we just discussed, the naive approach as well as the Markov chain, okay, that the score is a summation of all the previous locations, whether it was observed or not, whether it was normal that you have been there before or not. So that means both observed and unobserved locations. Unobserved are like a zero frequency problem again. Observed and unobserved. But we probably don't, to reduce false alarm, so we're not going to count and improve detection. We're going to look at unobserved locations only. So if you have been there, we are not going to contribute score to the anomaly detection. So we come up with two techniques here. That's STAD 0 and STAD 1. STAD 0 is just like naive. But only the unobserved locations are being counted. That means zero frequency type locations. That means you've never been there before. If you are suddenly somehow being there, we're going to add a score to it. STAD 1 is like Markov chain based on the Markov first order assumption. But again, we are only looking at unobserved locations. Okay? So more mathematically, basically saying that if it was not observed, then we have a score. Otherwise, we don't have a score. We sum all of them together. In the STAD 0 case, the STAD 1 case, similarly, that it was not observed that we have a score. Otherwise, it's zero score. And then similar mathematics, you get something like this. Let's look at experiments. So we presented 4 techniques. 2 are basically standard, naive, and Markov chain techniques. We introduced 2 other techniques, which based on unobserved locations only. We have, from a university, we have 500,000 hours of cell phone usage data. The data contains a cell ID, where the cell phone potentially is, or should be, the time, and basically time, location, and the identity of the phone. So we have these 3 pieces of information. We learned, for experiment purposes, we don't know actually which one was doing bad things or stealing phones or anything. So we assume all of them are normal. But in order to test our theory, that we train for each user, let's say X, and treat all the other people's behavior as masqueraders. So basically, we learn a model from an X, and then score the other one's behavior based on the X model. So basically, presenting user Y stole user X phone. Again, we already talked about the area under the curve. So the higher the number, the better it is in terms of performance. So we have investigated different false alarm rate from 1%. So FA equals 1 means the entire ROC curve. FA 0.001, that means a very small corner. Well, actually, very on the left side. So we want low false alarm rate. So, okay. So here you can see that in almost in 3 out of the 4 cases, that STAD 1 is doing better than the other techniques. Here, these are the 4 techniques that we just talked about. This is preliminary work, so we still have a lot to do to improve this. Another way of looking at it is that the equal error rate, when the false alarm rate equal to detection rate, where does it occur? And we look at this, that one is, this time is lower the better in terms of error rate, so we do better in this particular metric. Okay, in summary. So we presented basically 2 algorithms. There are sub-algorithms and stuff like that. LERAD is the first thing that we talk about, learning rules. Okay, we have the rule semantic is different from the typical classification and association rules. And we introduced the randomized algorithm back in 2003. We extended our work from network data to host data in 2005. And this year, we extended our work in terms of the validation step, weighting versus pruning. This is KDD 07. And secondly, we discussed the spatial-temporal anomaly detection problem and our preliminary results using a cell phone data set. Currently, we just obtained another data set using laptop. So hopefully, we get more results on different data sets, laptop, cell phone, and see how we can do. OK, I think that is the end of the talk. And if you have any questions, let me know. My website. Any questions? I was reminded that I need to repeat the question. Yeah.
Yeah, so in the scenario of the network data,
yes,
you consider different time periods and the oscillation on the traffic volumes? Like in some sites, the traffic during the weekdays is quite different from the one in the weekends. So does it affect what you believe to be the normal traffic behavior, the normality, and does it affect the false alarm rate?
Okay, good question. First of all, the question was whether the amount of traffic affects the model, as in that weekdays is higher traffic than weekends. So currently, the attributes involved in the models are based on the header and the payload. It does not have any traffic volume statistics in there or attributes at all. So we can easily put that in if we want to. So but currently, the attributes that we look at are based on actually the content of the traffic, not the volume of the traffic. So a lot of research does look at the volume of traffic. But you want to detect, I think in our case, we actually want to look at the payload. What kind of actually things that you are transmitting. So we don't want to go into the volume kind of thing. We want to detect actual real attacks. So kind of we try to look at actually the payload as well. Does that answer the question kind of?
Yeah.
And we can actually easily, well, I haven't tried it yet, but instead of using, or you can use both kind of attributes, right? In addition to content attributes, you can add volume attributes, okay? And in volume, and also that we can add like day of week, hour of the day, and stuff like that. So additional attributes. So right now we don't. But a second part of the question that you didn't ask that I didn't talk about, but addressed by some of the paper is the non-stationary effect of the traffic, so to speak. Okay. So over time, the content could also change. So how do we address that? And there's some work on that based on to deal with the non-stationary nature of the traffic. Yeah.
So the difference between STAD 0 and the naive Bayes model.
Yes.
Just reiterate that again. Was that
Okay.
basically you were not considering you hadn't been in the location and weren't considering, or you had been in the location and weren't considering?
Yep. Right here. So the question was that the difference between naive.
You're basically saying that you're just not contributing that. It's
Correct.
Depending on whether it's modeling or not.
Let me go through that real quick. So the naive is basically considering all locations, right? And multiplying them. For the STAD 1, some of these are observed, some of these are unobserved during training, like zero frequency, you never observe. Let's say LC was never observed before during training. So this would be counted. But LC minus 1, let's say that it was observed during training, this is not counted. So we only look at events that are that did not happen during training, instead of looking at both observed and unobserved. So just example, so this is unobserved, this is observed, then we don't count this. It's STAD 0, basically.
Can you go back to the results slide?
Yes.
So is there any difference between those two performance of the naive model?
For like very low false alarm rate, they are not performing differently at all. But if you look at here, that's kind of different a little bit. But we don't actually want to have really naive and STAD 0, right? We want it to be higher order. So again, this is very preliminary results. So we still have a lot of work to do on this. So I'm just presenting you basically a problem and potential solutions. And again, very preliminary results, not published. So
At this point, it's not
correct. But again, I want to emphasize that we probably don't want to go to naive and STAD 0 type thing. I'm just putting this up for illustration purposes. We are going to focus on kind of higher order stuff. Another potential problem here is that the way we calculate statistics might be off. So this result might not be totally reliable in some sense. Because I think the resolution that we calculate the time instance was like 10 seconds. We might need to go to resolution 1 second. 10-second resolution is produce fewer sample data points. If you look at resolution of 1 second, we have more data to estimate the population will be better. So here it's based on 10-second resolution. So I'm not too I'm not too easy about the 10-second resolution based on the data we have. So we need to kind of increase the resolution as well. Other questions? Yes?
When you were doing the pruning of your rules,
Okay.
You talked about doing it based on redundancy and said that you would keep the
More general rules.
More general rules. Now, it seems, intuitively, it seems like the less general rules are more likely to score well.
Oh, okay.
And I was wondering if you had ever tried things like maybe you prune it that way, but if you end up throwing out the more general rule later because of invalid results, that it might be worth putting the more specific one back in.
Correct. Yes, that's another way of pruning. You can reintroduce back the more specific ones. We thought about it as well. It's a little bit more complicated process. We went for a more easier approach that's weight them instead of kind of theory revision, as in that you make it more specific. So definitely that's another approach that we can take, but we just kind of chose to be a little bit easier in terms.
Okay, so you haven't tried it. Actually.
No.
You don't know.
That's something that we consider, yes. By the way, if you just think about that, we deal with a large amount of data. So if you do that, that means that, first of all, you have to keep track of all the rules that you considered before, as in more specialized rules. Somehow you have to sort them. And then you have to reevaluate them to bring them back, so to speak, and put them back, as in which one you want to pick up. So you involve with analyzing another round of training, so to speak.
Totally much harder.
Yeah, it's harder, but also more time-consuming. The point was taking is more time-consuming. When we're dealing with network data, you're talking about tons of traffic. You guys must know what tons of data mean. So we need to have some sort of fast, might not be perfect algorithm, but it needs to be fast and be good, but not perfect. We don't want to be perfect but slow. We want to be fast and good, so to speak. Okay. Yes?
Your attributes are ordinals rather than a metric. Is there an analogous investigation for something that has a metric? Location, if you say it's the cell, is an ordinal, but
Correct.
if it were actual coordinates.
Yep. That's a very good question. So far, we have been looking at quote-unquote discrete or ordinal type attributes. We haven't looked at actual location, like GPS, latitude and longitude type thing, which would be real values. In that case, there would be totally different types of algorithms, probably, because in probability, we usually deal with discrete events. We could deal with continuous events. However, then you need to assume certain distribution, like Poisson or normal distribution. So that's another thing that we can do. But right now, we are looking at only discrete values or ordinal values. We are not looking at continuous values yet.
It doesn't have to be continuous, as just that there's a metric. Distance matters.
Oh, I see. Distance matters. Yes. Actually, currently we don't have that kind of data, so we are not worried about it. If we got the data, definitely we will look into kind of distance. There are a bunch of algorithms that are based on distance. We can devise algorithms that anomaly detections are based on distance. Yes. We haven't considered yet. Well, one of the reasons we haven't considered it, we don't have our hands on data to investigate it. If someone can give me data, then definitely I would like to actually work on those. That's actually a more interesting problem than the kind of cell data type discrete locations. Actually, the data we have, the cell location, we don't even know what the respective location of the cell location. We cannot approximate how far the cell locations are from each other. So we were thinking about location distance, but we don't have that information, so we can't use it. So if there's data out there that I can use, that would be great. Any other questions? All right, thank you. Have a good lunch.